In this lecture, we will continue to discuss common source amplifier, but we will see a different version of common source amplifier, which is called degenerated common source amplifier. In this CS amplifier, the source is not grounded. We will see that there will be a resistor between source and ground. So putting that resistor between source and ground has certain effect on the amplifier behavior, and some of those behavior is desirable, some of them are undesirable. So we'll see that what are the advantage and disadvantage of degeneration. But before we visit the degenerated common source amplifier, we will discuss the simple common source amplifier and try to see that what is the maximum gain that we can get out of a single NMOS. So first we will discuss common source with current source as what is called load. So between VDD and the MOS, instead of putting RD, we try to put one ideal current source which will provide ID, the DC bias current required for the operation of this, and we will of course have our time varying input, and we will take the output from the drain. So again there is a DC at the gate which we are not showing, that will be ensured by some other circuitry, and in this case of course there will also be a DC, and there will be DC current which will be dictated. This ID will be dictated by the DC voltage at the gate. So we will see time varying voltage here, and we have supplied time varying input, and we will analyze this case for lambda not equal to 0. That means we are considering channel length modulation. That means R naught is there in the model of the MOS. So why we are doing this? Because we know that for CS with RD, the voltage gain was minus GM RD. This is what we derived. So here it says that if you want to increase the voltage gain, you will have to increase RD or increase the GM. So we are now trying to change this RD and try to see that what is the maximum voltage gain we can get out of one single NMOS. So we know that current source has infinite impedance, ideal current source. That means RD will be possibly infinite, in fact infinite. And in this case, we want to know what is the gain. So to solve this problem, that means find out the gain with current source load or current source biasing for lambda not equal to 0, we substitute the MOS by small signal model. So source is grounded here. At the gate we have Vs, and at the drain we are taking output. Since this current source is DC current source, so this will not appear in the small signal AC model, and this will act like open circuit. So for this part you can see that there is only one current, which is the DC, so that will not be included here. As I pointed out, there are two quantities, simultaneously present in the circuit: AC quantities, AC voltage and current, and then DC voltage and DC current. And one can study the circuit for each of them using superposition principle, of course assuming that the model of NMOS is linear, which is the case here. So now you can see that we want to know what is the output. So we know that 0 minus VO, voltage across R0, is going to be R0 into I0. But if you apply KCL at the drain, you see that this I0 actually is equal to GM-VGS. So KCL at drain, this gives I0 equal to GM-VGS. And here the source is grounded and gate is connected to VS. So this becomes GM-VS I0. Therefore, minus VO is equal to R0 GM-VS. So that says the voltage gain is VO by VS is equal to minus GM R0. Right. So we know that R0 is typically very large. So here you can see that the voltage gain is going to be very high. And in this case, you can see that both the parameters GM and R0, they are related to the NMOS. So this gain is, you can say, that the outcome of the NMOS alone. And that is why this is also called intrinsic gain of a MOS. So that means a MOS on its own can offer this much of gain. Now if you recall the result with RD and lambda not equal to 0. So for that case we had this circuit. So we had this circuit, and for this case voltage gain that we had obtained was minus GM into RD parallel with R0, of course for lambda not equal to 0. Right. So here what you can see is that the expression that we have got here from the previous analysis can be also obtained from this result. So how from here we can arrive at this equation 3. So 4 leads to 3. So how this can be done? So here we can interpret this term as the output impedance looking into the drain. And this output impedance, which we obtain by applying a unknown voltage source here and then finding out how much current it drives. So we can see that this current will take two paths, one in this direction and another in this direction. So this current basically gets splitted into, say, I1 and I2. That means you have a circuit like this between drain and ground, and then you have another circuit here between drain and ground. So the impedance that you will see looking into drain, which is the output node, will be the parallel of impedance offered by this part of the circuit and this part, and these two both are in parallel, right? So now if you analyze each of these two circuits separately, so the impedance offered by the upper part is of course equal to RD. So the impedance in this direction is RD, and impedance looking towards this MOS from its drain is going to be R0. So this impedance that you see from this side is basically parallel of RD and RO, and that is the impedance that appears here. So this result is very general. This not only leads to this result 3, but this also leads to the AB is equal to minus GM RD, which we got in the very beginning for lambda equal to 0. That means without channel length modulation. So in that case, if you try to find out the impedance R2 of a MOS without channel length modulation, it will turn out to be infinite, while the impedance of RD remains RD. So that is why we have RD here. And the case that we analyzed just now, in this case, now you can see that if you put a current source here, which we have done here in this case, then the impedance of this current source is infinite. So we have now infinite impedance in this direction, and in this direction we have impedance R0. So the parallel of these two is of course going to be R0, and that is what we have got here. So for this simple case, common source with RD with lambda is equal to 0 or lambda not equal to 0, or with current source, all the results, they actually come out of this general result that we have got here, right? So here we see that the maximum gain that we can get out of a single NMOS is minus GM R0, and this is going to be very large, and this happens when we have uh, ideal current source for the biasing, or as a load. It is also called as a load, but typically very often we will be connecting our external load here. So this is with the NMOS. Now we have already studied PMOS also. So one would like to see that how to implement a common source amplifier in all these configurations using PMOS. So we will now see PMOS common source amplifier. So recall that for PMOS, the source should be at the higher potential compared with the drain and gate. So for the common source, we must have this orientation of the MOS. So this is in terms of voltage also. This has to be at higher, this has to be at lower, and then we will have this usual gate. So here also, of course, the AC will be applied at the gate, and the output has to be taken from drain. So this is the uh, topology for common source amplifier. That means source remains sort of unused, or it is there in the both input and output loop, and then only gate and drain are being used. So once we have labeled or connected our input and output to the MOS, we now have to decide the biasing or the connection of the, you can say, load. So in the simplest version of the common source amplifier, source is grounded, S is grounded, and keep in mind that this grounding is basically the AC grounding. It need not have 0 DC, the source, but for AC it should be grounded. So that can be done. So there one requirement that source should be at higher voltage compared with the gate and drain, and at the same time it should be AC grounded. That means its voltage should not change with the time. So this can be very easily fulfilled if we connect the source directly to the DC VDD. So now you can see that both the requirement, that source at a higher voltage and source voltage not changing with the time, is getting fulfilled here. Now there will be drain current flowing through this because of the DC available at the gate. So we should provide a path from this DC source to the ground. That means there should be a ground here, and there will be the DC current ID flowing through it. Now we have to take our output from the drain. So we cannot connect this drain directly to ground, otherwise output will be always zero. So we will have to isolate this drain from the ground so that output gets decided by the time varying input. At the same time, there is a path for this current to flow. So now that can be done very easily by putting one RD. So this is the common source amplifier using PMOS. Now its current source version can also be implemented simply by substituting this RD by a current source like this and taking output in this way. So this is the common source, PMOS common source using current source biasing or current source load. Right. And if you analyze these two cases, the formula for the gain of these two cases will also be exactly same as this. Only difference is that now this GM will be for PMOS. So instead of normal GM, actually which is GM for NMOS, you will now have GMP. So this will be for PMOS, because we know that this GM depends upon mobility of the charge carrier. So here will be mu P, here we will have mu N. So this is going to be the difference. So now we see that with the current source biasing, we can have a more gain. So question will arise that how in real life, suppose we want to implement this version of the common source, then how do we implement this? So for this case, we will have to take the help of MOS, because we have already seen that ideal MOS has this behavior. That means if you maintain constant gate to source voltage, if you keep this VGS fixed, then ideal MOS will provide a current ID which will be fixed and decided by gate to source voltage. Right? So ideal MOS can be used as a current source with value ID decided by the gate to source voltage. But in the real life, we have seen that there will be slight increment in the drain current with the drain voltage. Okay, this is the practical case, or the case with channel length modulation. So this is for no channel length modulation. Now if we include channel length modulation, then what happens? Then this MOS even when we have fixed GS, for the fixed GS, it is not going to give rise a fixed current, but it will have a current which will vary with DS also. That means drain to source voltage, the voltage across the current source, which should not happen in ideal current source. So this MOS can be represented like this. So we know that we had included this R0 for the current changing with the drain to source voltage. So this was there to account for this increment in the drain current with the drain to source voltage. So this practical MOS actually can be represented in this way, where this MOS is now ideal. So we have a ID current flowing through this, which will be given by same formula as this one, and then we have additional current arising because of R0. So in this case, the current source actually becomes like this: ideal current source in parallel with a resistor R0. ID. So where ID will be 1 by 2 mu n COX W by L VGS minus VTH whole square. So in the both the cases, for lambda not equal to 0 and lambda equal to 0 and not equal to 0, ID is this one, and the additional current here will be contributed by R0, which will be decided by the drain to source voltage. But in this case, drain to source voltage has no effect on the net current. Right. So now the common source amplifier with the current source can be implemented with the help of MOS. So now we want to implement this current source using MOS, but keep in mind here that the source, if we try to use NMOS for this current source implementation, then this source voltage is not going to be fixed. Source voltage will vary with the time varying voltage applied here. So in this case, this current source cannot be replaced by NMOS version of the current source, because keep in mind we will have to keep the gate to source voltage fixed. So in this case, what we will have to do, we will have to use a PMOS connected to VDD, and then here if you put this gate voltage fixed to a certain DC, then this will imply fixed GS, and then this will act like a current source. Right? Keep in mind that in the PMOS, the current actually flows from source to drain. Holes also flow from source to drain. So the direction of current is going to be from source to drain. It is not going to be from drain to source. So this circuit, let me show it more clearly. In real life will be implemented in this way. So this will be at certain fixed gate voltage, and here we will have DC gate voltage in addition to time varying voltage, and then we will be taking output from here. So this is CS with current source biasing, and in this case now you can see that the current source here does not has infinite impedance, rather the impedance is equal to R0. So here we have ideal current source in parallel with a very large resistor, and this large resistor is going to be the impedance of this current source. So in this case, the gain, if you try to work out using small signal model, will turn out to be AV is equal to minus GM into this resistor in parallel with this resistor, and this R1 is R0, say N, because this is NMOS, and this is going to be equal to R0P. This is PMOS. So minus GM into R0N parallel with R0P. Right. So this formula we will keep in mind. This is very useful. This is generalized version of many of the simple cases of the common source amplifier. Right. So in all the cases, we have seen that one characteristic that is always valid with the circuit is the source is always grounded. Right. So now what we are going to do, we are going to change this condition. We are going to put a resistor between source and ground and then try to see that what we get, what is the gain and what is the behavior of that circuit with respect to this simple version, which is this is called without degeneration. So we will again start with the simpler version. That means we have resistive biasing. So we are now going to make one change in the convention. We will now onwards calling all these time varying signal as VI rather than Vs. And this we are doing because now there will be a time varying voltage at the source also. To distinguish that source voltage with the external voltage that we are applying, we will be now labeling all the external input which we want to amplify as VI. So input voltage, the AC input voltage will be designated now onwards as VI, and the AC output voltage remains VO. So this resistor is RD as usual. This we will be calling as RS. So for this case, we want to know what will be voltage gain. So circuit is now more involved compared with the previous cases. And here also we will start with the simplest model of the MOS. That means first we'll find out AV for no channel length modulation. That means infinite. So we substitute our MOS by the model. So this is our MOS, and now we find that there is a resistor between source and ground. So we put this source resistor, and there is resistor between drain and AC ground. So this is a equivalent AC model. Model of the above circuit. So in this circuit, we have to find out ratio of output to input. So we can assume or label these currents. So this is IO and this is say IG. So we apply first KCL at drain. So where we get IO is equal to IG. So this gives minus VO by RD equal to GM VGS. And we know VGS is VI minus the voltage time varying voltage at the source Vs. So this becomes minus Vo equal to GMRD into Vi minus Vs. So we need to find out what is the voltage at the source. So we can now apply KCL at the source to find out Vs to set up another equation. So when we apply KCL at source, we see that the Ig again comes here at the source. So this Gm VGS is equal to the current that flows through this, which is Vs by Rs. So we have here equation 5. So from 5 and 6 we can find out what is Vs. Five and 7 imply so this is Vs is equal to minus Rs by Rd into Vo. So this we can substitute in equation 6. Minus Vo equal to Gm Rd into Vi plus Rs by Rd Vo. So when we take Vo on one side, we have 1 plus Gm Rs equal to Gm Rd Vi. So the gain Vo by Vi becomes minus Gm Rd divided by 1 plus Gm Rs. So we are familiar with this numerator expression minus Gm Rd. This was the gain of common source amplifier with resistive biasing or resistive load. This one. So the gain of this is here in the numerator, and the denominator is always positive because Gm is positive, Rs is positive. So we see that we have a gain for degenerated case AB with say degeneration of the common source amplifier, and this is less than AV without degeneration, right? Non-degeneration, let us say. So first reaction would be that why to go for the degeneration when the gain is less than what we were getting earlier. So certainly looking from only gain point of view, this circuit is not good, not beneficial. But then gain is not the only parameter that we try to obtain from MOS. There are various other things that we expect from amplifier, and we will see that in many cases reducing gain will be desirable. So now let us see that why this reduced gain case also will be better. So for that, we will revisit this MOS, and now we will try to see that what happens to the output signal when input grows. Right? So let me try to show it here. So we now explicitly show the DC part also at the gate and the AC part, time varying. So this DC part will lead to a DC current ID, and so when this input is not there, we have this DC current flowing through this circuit that will lead to DC voltage VD at the drain, right? So now if you see all these voltages, then what you are going to get is, this is time axis and we are simply plotting all the voltages. So what will happen is the maximum voltage that appears in this circuit is VDD, and the smallest voltage that occurs is this ground, which is here. So all the voltages that you will see in this circuit will lie in between this floor and this ceiling, right? So here we see that we have a drain voltage here. So drain voltage could be somewhere here like this, DC drain voltage. Now when we apply the time varying voltage here, so on the input side condition is going to be like this. This is your DC gate to source voltage, and on it you will be putting the time varying input. So your condition at the input is going to be this. So net gate to source voltage will be sum of these two, and we know that net gate to source voltage should be always greater than TH for this transistor to be in for the channel to exist. And for saturation, we will have to fulfill additional condition that net gate to drain to source voltage should be greater than VGS minus VTH. So this is the additional constraint that we will have to ensure. So when this input is applied at the gate, we know that there will be time varying voltage resulting from the time varying current flowing through this RD, and the net drain voltage will have this kind of behavior, right? So here you see that this is the meaning of amplification. If you have certain amplitude here, say Vp, what you are going to get here is AV into Vp, a more swing or the more amplitude at the drain. Now you see that what will happen. Suppose we increase this amplitude. That means now you take a larger signal like this. So what will happen? This will also get enlarged, right? So suppose we have already taken such a large input so that on this side we have started touching this ceiling, and this is the maximum voltage that you can get, and corresponding to this maximum voltage uh, you will have here the minimum current. This current is going to be minimum because for this maximum voltage you can see that gate to source voltage is very small. That means the net drain current will also be very small. So the minimum value of this net drain current is 0. That means the maximum voltage that you can get here will always be VDD. You will never get a voltage more than VDD. So now if you further increase your input here, suppose you still have scope of increasing the input and yet maintaining this condition, then here you can nevertheless increase your input. But what will happen here is on the lower side you will still have room to grow possibly, but on the output side, upper side, you will get a flattening here. So you will get output which is clipped version of the sinusoid, upper clipped version. So we say that there is an input. If you go beyond that, then the output will start getting distorted. Right. So now if we plot input versus output, this is the input time varying input amplitude and the time varying output amplitude. Right. So this graph we know that will be related by VO is equal to AV into VI, the gain of the amplifier. Y is equal to mx. So we'll have this kind of graph. And here, if your DC gate to source is such that you are getting this much of DC, so that this range from the VD to VDD is smaller than this one, then this is the maximum undistorted output you can get. So there will be maximum output that you can get without any distortion. Here, this is going to be the upper limit of the output without any distortion. So now if you have a large gain, say for example this scenario, then this will definitely hit this upper limit for certain VI. Let us say VI1. That means if you increase your input here beyond VI1, then the output will start getting distorted. And we never want that to happen. So what we will have to do is either keep the input smaller, or either you keep the gain smaller. So keeping the input smaller might not always be possible, because input is coming from previous circuits, and which is already maybe say amplified to certain level. So this need not be disturbed. So input should not be allowed to be or forced to be smaller. What we can do, we can rather what is called sacrifice the gain, and we can design an amplifier which has this kind of gain. So this will be AV, say D, and this previous one we will call as AV and D. So this is the gain for ND case, the normal case, or actually non-degenerated. Let me be specific that why I am saying this. Non-degen CS, and AVD is degenerated CS case. So here we see that if we sacrifice the gain, which we have seen is happening in the degenerated case, gain is smaller than the non-degenerated case, then you will be able to handle larger input. Of course, it will not be amplified to that extent, but still you will be able to amplify. Right? So here we see that this formula for the gain is of y is equal to mx, and this equation is a linear equation. Superposition is valid here. So we say that when we sacrifice the gain, we increase the linearity. That means the increase the range of the input over which equation will be of linear type, y is equal to mx type. So here, so we see that degeneration increases linearity range, and keep in mind this linearity range is being talked about with respect to the amplitude of the input. In the one of the previous classes, when I talked about the linearity, I talked about the linearity with respect to the frequency, because input will be say Vp sine omega t. So here now we are focusing on the amplitude behavior of the amplifier. So we increase the linearity range by sacrificing the gain, voltage gain, right? Or we trade off we trade off linearity with the voltage gain. So this is the, now you can see that advantage. So the reduction in the gain which was appearing as a disadvantage of the circuit is now advantageous from another point of view, right? So we derived the gain expression, we found this thing and we found it is less than, and then we tried to see that why it is not such a bad thing to have this kind of gain behavior. Now what we will do, we will try to see qualitatively that why gain should get reduced. So mathematics says that it gets reduced, but qualitatively why it should get reduced.
Sir, hello, sir.
Yes.
Sir, I have a doubt, sir. You told that we have two options. Either we can keep VI small, or we can keep AV small. So, sir, why we are making VI small?
No, that is what I am saying, that suppose you don't want distortion to happen, then you can keep your input small. You will be forced to keep the input small, otherwise distortion will occur. But suppose you have no control over the input, right, which will happen in very often many of the real life scenario, this you will not be able to control, then sacrificing gain is the only option, because no one would like this distorted output. Everyone wants exact replica of the input on the output side also. So if it is sine, output should also be sine, not the clipped sine. Okay, so now let us qualitatively try to get a feel that why gain should get reduced. So here you see that the circuit says, this circuit says from here or even from here also, you can say that the output is basically decided by the current, time varying current flowing through this RD. And the current flowing through this RD is basically equal to GM into VGS. So if the output is less for the given input compared with without degenerated case. So here we have two circuits, without degeneration, degeneration. So gain of this is less compared with this circuit. That means if you keep the input same in the both the circuit, output here is going to be smaller compared with without degeneration, right? So this is the meaning of gain reduction. Now, since the output is decided by current flowing through RD, that means in this case, the current through RD should be smaller than the without degeneration case. That means this number should be GM into VGS should be now smaller compared with the without degeneration case. Now let us see that whether that is happening or not. So you can see that that will happen. Uh, so we can calculate VGS. So with the degeneration case, VGS is VI minus VS. This VS is this current flowing through RS. So VI into GM VGS into RS. So this says that VGS into 1 plus GM RS is equal to VI. So here VGS becomes VI divided by 1 plus GM RS. Now if you take the non-degenerated case, so if you see the model of this, source is grounded and gate is to input. So in this case, your VGS is going to be equal to VI. But for the degenerated case, you can see that VGS is smaller by factor 1 plus GMRS. So here what happens is, since the VGS gets reduced for the degenerated case, so of course the current is also going to get reduced. So that is why the output voltage that you will see will be smaller compared with this case. So this degeneration leads to reduction in the gate to source voltage. So again, this explanation is from mathematics, but now qualitatively also from this circuit itself, we can guess that that should happen, because here what will happen is when you increase the when you have certain input, whatever input is there, so that will produce time varying current Ig, and that time varying current will produce now a time varying voltage Vs at the source, which is zero in the undegenerated case. So since now there is a certain positive voltage, time varying positive voltage at the source, so net gate to source voltage is now going to be smaller compared with the undegenerated case for the same input which we are applying to the both the cases. So since the net gate to source voltage because of this resistor is smaller, so obviously the net time varying current that will be produced by MOS is going to be smaller, hence the output voltage is also going to be smaller. So this is a qualitative explanation that why putting RS will ultimately reduce the gain. So RS produces voltage that reduces the gate to source voltage, net gate to source. So that reduces the net this voltage current. So that leads to reduction in the output voltage also. And here this drain current is dictated only by the input. Source has no role. So this is what I pointed out in one of the classes. It is the gate to source voltage, which is the input quantity to MOS. But in some of the scenarios like here, a source also comes into existence, source voltage. Although here we have put a resistor deliberately, in some cases there will be certain other circuitry which will inevitably play the role of RS. So now one question that can be asked that how to implement this RS using MOS, because we have already seen that if we substitute this RD by current source, then how to implement that current source using MOS, because in CMOS technology it is desirable that everything is implemented using MOS, then it becomes easier. So for that we will study what is called diode connected MOS. It is that MOS which can be used to implement small resistors also. So for RS we can use this MOS. So here we have a diode word. So this connection of MOS is given by this configuration. So we short circuit gate and drain. So this is the diode connected NMOS. Now why this one is called diode connected? Actually the naming has been derived from that of the corresponding BJT connection. So in BJT also we know that this emitter is equivalent to source, collector is equivalent to drain, and base is equivalent to gate. And the structure of BJT, NPN BJT, we know is like this. This is N, this is P, this is N. So this is your base, this collector is here, and this emitter is here. And we know that there are two PN junctions in BJT, collector to base and then from base to emitter. Now here if we short circuit collector and base and have only the collector and emitter nodes available to us, then you can see that here the effective junction that will be getting implemented is this PN junction, base to emitter PN junction. So this circuit or this structure now behaves like a diode. So here you have this P, and here you have N, and this is your emitter, and here you have collector. Because any current flowing from here will be now dictated by this junction. The current will not flow through this, it will take this path, right? So this part is useless, it will have no role in deciding the current. Current will take easier path, which is directly from base to collector. So for all practical purpose, now situation is like this. And of course base is also here. So this is collector or base node. Now you can see that this is simply like a diode between collector node and emitter node. So BJT can be made to operate as a diode if we short circuit the base, which is the controlling node for most of the purpose, with the collector, which is typically the output node. Now if you come to MOS, then here controlling node is gate. So if we connect the gate with the drain, which is the usually output node, then we have same connection here. But keep in mind that this does not lead to a PN junction kind of behavior, right? So the similarity ends here. This similarity is not up to this level, right? But the naming convention has been borrowed even from here to here. So this is not, so here BJT becomes equivalent to a diode. However, this is not equivalent to a diode. Yet this is called diode connected because of the corresponding BJT connection, right? So now we will try to see that if we have a diode connected MOS, then what is the impedance between these two nodes? So this does not behave like diode. So let us see what is the behavior of this MOS. So for that, we will try to find a small signal model of this circuit. So this is MOS, and now what has been done is gate has been connected to the drain. So this connection has been done here, and now we want to know what is the behavior of this circuit, resulting circuit. That means impedance between these two nodes. So we want to treat it as a black box where we have drain node coming, source node coming, and we want to know the impedance. So let us connect a external voltage source Vx, find out Ix, and let us see that what is the impedance between these two nodes. So this is GM VGS. So here you can see that clearly I is equal to GM VGS. GM, and now you can see that gate is connected to drain, which is connected to the source, and source is anyway connected to the external source. So you can see that this Vx is same voltage between gate and source. So this is equal to Vx. So this implies Vx by Ix is equal to 1 by Gm. So conclusion is that if you have diode connected MOS, then it behaves not as a diode, rather it behaves like a resistor whose value is 1 by Gm. So why I pointed out this application of MOS is that now in the common source configuration, you can put MOS in place of the RS. Like this is now equivalent to RS, and we know that its value will be given by 1 by Gm. So this is say MOS 1, this is MOS 2, so this is how you can implement the degeneration in real life.